The two fundamental algorithms for graph traversal were depth first search, or DFS, and breadth first search, or BFS. And we saw that with breadth first search, we could find the shortest path from a starting node to all other nodes in an unweighted graph. But what if we have a weighted graph? So for example, what if these were cities and the edges that connect them represent flights from one city to another, and the cost is the dollar expense to go on any given flight? Or alternatively, what if these were cities and edges represented roads you could take between cities, and the numbers, the edge weights, represented the cost it would take in gas or in mileage or of some sort to traverse between those two cities? And we want to find the shortest path to get from our starting city to any other given city. So we could use Dijkstra's algorithm, this is pronounced Dijkstra, to find the shortest path between a starting node and any other given node in a weighted graph. Before I start Dijkstra's algorithm, I want to emphasize that Dijkstra's algorithm requires the graph to have every single edge have a positive weight. So Dijkstra's algorithm does not necessarily work in graphs that have negative edge weights. Zero edge weights actually would still work, it just can't be negative. First, we have to set all nodes' distances to infinity and set our starting node's distance to 0. So our starting node is 0 distance from itself. Each of the other nodes, we're going to start as infinite distance so far. And then the key difference between Dijkstra's algorithm and DFS and BFS, really all three algorithms are essentially fundamentally the same, except breadth first search uses a queue, depth first search uses a stack, and Dijkstra's algorithm uses a priority queue. It's a min heap with respect to distance. So the lowest distance is the highest priority. Over here, I'm just going to be drawing my priority queue. I'll kind of space it out because I'm just going to keep it as like a sorted list, but behind the scenes, you would probably use a heap to implement it. So each of the tuples that I'm going to be representing are distance node tuples. So I'm going to add 0 start to my priority queue. My starting node is A. In my priority queue, top will be smallest, bottom will be largest. So top is highest priority. So I will add 0, A to my priority queue. So while the priority queue is not empty, it's not empty, I have a node here, pop the current distance and the current node from the priority queue. So I'm going to pop the current distance, current node from the priority queue, which is distance 0, current node A. So distance 0, and I'm at node A. If the current node is not done, nope, it's not done, mark it as done. Cool. So that means that I've found the shortest path to A, which is length 0. And for all outgoing edges from my current node, so the edges I'm writing as the starting point of the edge, the ending point of the edge, and the edge weight. So for example, this edge would be AD3, right? So each of the outgoing edges from my current node, if my current distance, 0, plus the edge weight, let's do D first. So if 0 plus 3 is less than D's current distance, it is. D's current distance is infinity. 0 plus 3 is less than infinity. Okay. W, so the neighbor, D's current distance is D plus E. So the current distance is actually 0 plus 3, which is 3. W's previous node is cur, so D's previous node is A. So I'll just write it above. And I add D plus E, so 3, comma W, so the neighbor D, to the priority queue. I add its current distance and the node itself to my priority queue. Cool, so that was the first outgoing edge from A. The next outgoing edge, let's just do this one, A to C. If D plus E, so if the distance to my current node, which is 0, plus the edge weight, which is 6, so D plus E, 0 plus 6 is 6. If this is less than W's current distance, which is infinity. That's true. 6, so 0 plus 6 is 6. 6 is less than infinity. Okay, so I enter. W's current distance becomes d plus e. So C's current distance becomes 0 plus 6. So the current distance becomes 6. W's current node becomes, W's previous node becomes the current node, so C's previous node is A. Just write it above. And I add d plus e, so I add 0 plus 6, in case 6, and the node itself, C, to my priority queue. Again, I'm writing them spaced out because this is going to be a priority queue and I want to have them sorted. So I want to leave space for future insertions to kind of go in the middle because I want it to be smallest to largest. I've added to the priority queue. Now I go to the next edge. So the last edge from A is A to B with edge weight 1, right? A to B with edge weight 1. If D plus E is less than the current distance, so 0 plus 1 is less than infinity. Okay, so I enter. The current distance of W, so the current distance of B, is D plus E. So the current distance of B is 0 plus 1. B's previous node is the current node. Okay, so B's previous node is A. And now I add D plus E, 0 plus 1, which is 1, 1, comma, B. So the priority queue is not empty. I pop off 1B from the priority queue. So my current distance is 1, D is 1, and my current node is B. I'm currently at B with distance 1. If cur is not done, no, cur is not done. Okay, I enter, mark cur as done. Yay, B is done. Let me make that more like a check mark. So that means that this is the true previous node and total distance from the start. I should have marked that here as well. Basically, the moment I mark something as done, I'm saying, hey, this distance and this previous node are finalized. A doesn't have a previous node because A was my starting node. Okay, so let's continue. So mark cur as done. I've marked it as done. This is the previous node and the distance from the starting point. That is set in stone. Okay, for all outgoing edges, current node, so B, neighbor, and edge weight. So the only outgoing edge from B is this one. So B to C with edge weight 4. So if D, so D is 1 plus the edge weight 4, so 1 plus 4. If 1 plus 4 is less than the current distance, so 1 plus 4 is 5. C's current distance is 6. 1 plus 4 is 5 is indeed less than 6, so this is true. I enter. W's current distance, so C's current distance, is D plus E. So the current distance is 1 plus 4, which is 5. And W's previous node is cur. So C's previous node, I'm going to set to B. I've just found a better way to get to node C if I go through node B. That better way will have a distance of 5 from the. Okay, and now I add D plus E W, so 5C to my priority queue. So I add 5C to my priority queue. Now, before I go any further, I want to point out you might be weirded out by this. You might be like, whoa, why do I have 2 different elements labeled by C in my priority queue? And the reason for this is that in Dijkstra's algorithm, I have no idea if I've found the best path to a given node until I pop that node off of the priority queue and mark it done. So originally I had 6, C in my priority queue, but now I found a better way to get to C, which has been added higher priority in my priority queue than my original one, because this is a better path. So we can indeed have duplicate nodes in our priority queue. We could theoretically have one element in our priority queue for every single possible edge in my graph. Who knows? So the fact that we have these duplicates is totally okay, and it's expected. It means that I've now found a better path to a given node. So I found a better path to C. Okay, so let's continue. So this is where I left off. We added it to the priority queue. Awesome. Go back to my while loop. While the priority queue is not empty, it's not empty. I have 3 items left. Pop the next item from the priority queue. So D cur is 3D. So current distance is 3. Current node is D. So I'm currently at D. If cur is not done, no, it's not done. I don't have a check mark. So I enter, mark it as done. D is done. And this is the best possible way to get to D. I can get to D by going, so the previous node is A, and my overall distance from the starting node is 3. That was the best possible way to get to D. That's finalized. I've circled it, it's done. Okay. For all outgoing edges coming from node D, so node D only has one outgoing edge. It's D to C with edge weight 1. So for this edge, if D plus E, so if 3 plus 1 is less than C's current distance, which is 5, so 3 plus 1, 4, is less than 5, that's true. I enter the if statement. W's current distance, so C's current distance becomes D plus E, it becomes 3 plus 1. So C's current distance becomes 3 plus 1, which is 4. C's previous node is D, so this means I found another better path to get to C. This time, if I came from node D, I would get to C with a total length of 4 from the start, which is this. That makes sense? Okay. And now add D plus E, so add 4 comma C, the current neighbor, the neighbor that I'm looking at, to the priority queue. 4 comma C. So this is another way to get to C, this time with distance 4. And again, I'm going to pause before I go on. Notice I've added yet another instance of node C to my priority queue. This is absolutely fine. This means that I found yet another better path to get to node C. Totally fine. Okay, next iteration. While the priority queue is not empty, it's not empty. I have 3 things in my priority queue. Pop D cur from the priority queue, so distance D is 4, current node is C. If the current node is not done, C is not done, I don't have a check mark, mark the current node as done, and that means I've finalized my best way of getting to the current node. So the best way to get to node C is coming from node D, and that would result in a total path distance of 4. For all outgoing edges coming from my current node, well, C doesn't have any outgoing edges, so I do nothing here. So I finished this because I did not enter this loop because C does not have any outgoing edges. I could go back to my while loop if I wanted, but I want to point out one thing. Even though my priority queue is not empty, right? I have 2 things left in my priority queue. I know in advance that I've visited every single node. And I could keep track of this in constant time with respect to my algorithm by just having a counter of how many nodes I've completed, right? I could have had a number of visited nodes counter that starts at 0, and every time I mark a given node as done, I would just increment that counter, and the moment that counter equals the total number of nodes, I would know that I've visited every single node. So if I wanted to, I could exhaust the priority queue, just pop off the next thing. It's not done, so I don't, it is done, sorry. So I don't enter the if statement, then while loop, pop off the next one. If it's not done, well, it is done, so I do nothing. I could keep going through the priority queue if I wanted, or I could just terminate early. I could realize I've already visited, so back here, I could realize I've already visited all my nodes. There's no reason for me to keep iterating over the items in my priority queue. I'm just gonna stop right here. No need to do anything further. I'm definitely done. So this is Dijkstra's algorithm, and let's take a look at what we've gotten. So we know that if I start at A, the shortest path to get to A is just the node A, which has a path length of 0. Okay, that's kind of obvious. The shortest path to get to node D is I come from A, and I have length 3. So I'm going to mark the shortest path this color. So getting to A, it's just itself with length 0. Getting to D, I could have come from A, and that path has length 3, which is correct. It has length 3. For node B, I could have come from A, and that path has length 1, which is correct. This path has length 1. And for C, I could have come from D. I'm only keeping track of the previous, and I now know the whole path because D also kept track of its previous. But yeah, I could have come from D to get to C, and that total path would have length 4, which is correct. Even though this last edge has length 1, the whole path had length 4. And I've ignored these two edges in my output because these two edges don't help me. They don't give me a shorter path to node C. So I found the shortest path to get to every single node starting from node A.